And I have to ask you a few questions. The first is to give some highlights of your talk, just to be understandable by the general audience. So let's start from that.
Okay, so I talked about possible connection between two scales in nature. So one scale is the scale which is associated with gravity, and this is a very, very small distance scale, which is what, 10 to the minus 33 centimeters. And yet another, and this is the scale at which we think the quantum effects in gravity are important. And then I talked about another scale in nature, which is kind of particle physics scale, which is reached at colliders such as LHC or previously LAP, and which is associated with the weak interactions, and this scale is of the order of 10 to the minus 16 centimeters. And the question which I discussed, it could be perhaps that one scale might be related to another. And so if we are given one scale, then perhaps with some theoretical computation we can find yet another scale. So that was...
Yeah, this is a very interesting scenario, and I am also in favor of that, by the way. Well, the next thing I would like to ask you is what is your impression of what we are doing here? Of course, you have been only one day, but...
Well, for me, this is first conference after almost 2 years break. So I myself enjoy very much just sit, looking at friends and
this is nice environment, right?
Yeah, this nice environment, and the people who we only meet in via Zoom or virtually, and now we can talk, we can really communicate. So this is completely different thing.
Yeah, we are very happy that we could do it. I mean, as you see, we took special measures to be outside and inside.
So I'm very happy that this conference was organized and attracted.
Many other things are only online, as you know. And we have several meetings. We have 8 meetings. So the last question, let's say, is what you would be, as an experienced and successful scientist, your suggestion to young scientists who start their career and in research?
No, I think that we live at the very interesting time in particle physics when the standard model, which was confirmed experimentally, but still there are different puzzles, observational puzzles, which were not resolved, and there are many ways in which we can go, and so now it's kind of right time to think very wide, to see where the particle physics will go. So perhaps we can even compare this time with the old time of 100 years ago, where people thought that the physics is finished, but then a new direction showed up. So perhaps we are at that time.
It's great to be at the first conference after almost 2 years of Zooming. Okay, so thank you very much, organizers, for making this meeting possible. So what I would like to discuss here is a possible connection between the Fermi and the Planck scale. Okay. There was a message that there is no sound. Okay. Okay. So first of all, I would like to tell you. So the work which I going to describe is done in collaboration with several people, Andrei Shkern, Sebastian Zell, and also myself and Andrei Shkern, and here are the relevant references. The outline is the following. So I'm going to start with the discussion of standard model and conformal symmetry. And then I will tell you that there may exist a non-perturbative connection between the two. Then I come to conclusion. So, if you look at the standard model, at gravity, then we know that there are, I would say, at least three scales in nature. So first of all, the biggest scale, it's the scale of quantum gravity, which is related to Newton constant and to the Planck scale. Okay, so that's the biggest one, 10 to the 18 GeV. The next one is the scale of particle physics, which we all know about, and this is the Fermi scale, which is associated with electroweak symmetry breaking, and which is about 80 GeV or 100 GeV, depending the particle you choose. There is yet another scale which we observe, which is associated with accelerated expansion of the universe, and this is perhaps the smallest scale which we observe, which is the scale of vacuum energy or dark energy, whatever we name it. The question is, are all the scales related, or are these all scales independent? And what I'm going to do in this talk, I will try to argue that perhaps the electroweak scale can be derived from the Planck scale, though I have absolutely no idea from where the scale of cosmological constant or dark energy is coming from. Anyway, the Coleman-Weinberg idea doesn't work. Okay, of course, the idea was so attractive that people tried to change the standard model, add to it different other particles, and then in principle it may be working. However, we should look at the following issue. In all these considerations, we didn't take into account gravity, okay? And gravity, it breaks scale invariance, it breaks conformal invariance. Why? Because it comes with the parameter in plan, okay? So we can wonder why the gravity was not accounted at all in all these Coleman-Weinberg exercises. So there is actually the rationale behind that. If you again consider gravity perturbatively, if you apply to gravity okay, then all corrections coming from gravity are suppressed by the Planck scale, so that this equation remains in force, and then gravity corrections are small. Okay. Now the question which I'm going to discuss is perhaps if perturbative contributions from gravity are small, perhaps there are non-perturbative contributions which can bring the Planck scale in force and break in some way electroweak symmetry. So I want to consider a scalar field which is very large, much larger than the Planck scale. Okay, and if you look at the theory at the scalar fields, then we can neglect the Planck scale and get this action. And that's an interesting action because this action is, first of all, scale independent. And secondly, in this action, the Planck scale is dynamical and is proportional to the large field phi. Okay, so in order to account that, it's better to do computation with in what is called the Einstein frame. And Einstein frame is the frame in which you remove dynamical dependence of the Planck scale on the field phi and make it constant. Okay, so one can go to Einstein frame by doing some nonlinear transformation of the scalar field. But what is interesting in this nonlinear transformation is that at large values of phi or at large values of I, this field phi is an extremely nonlinear function of a new field. So it contains exponential. And what does it mean? This means that if you look at this path integral, then because of this extremely nonlinear connection between the field in Einstein frame and the Jordan frame, the action gets another piece, which is proportional to the field itself. Okay, and what does it mean? That means that when we look for the saddle point of this action, we should not just minimize the original Euclidean action, but we have to take into account the source. Okay, and this type of things are not unusual. Okay, so for instance, if you compute even this type of integral for a large n, and this is one-dimensional integral, when n is very large, you better exponentiate this guy, and then you get a correct saddle point. If you just ignore this prefactor, then your expansion is not going to work. And then there are other examples. So everything else is just straightforward. Okay, so you take this action, you take the maximal of 4 symmetric metric, you write down equations of motion. There are extra pieces associated with this boundary term. An important point here is whether semi-classical parameter appears, whether you can do these things at all. And you can check that indeed, if you look at the action, you make some rescaling of your variables, then the parameter square root of psi goes out of the total action, meaning that it can be considered as analog of 1 over h bar in WKB approximation. Okay. Because of the presence of like delta function terms, everything gets singular. However, this singularity can be regularized by higher dimensional operators. Okay, so this is an example of higher dimensional operator which can be added to the action, and then everything gets finite. And then you ask yourself, okay, can you choose different parameters in your theory in such a way that indeed the vacuum exploitation value of the Higgs field is exponentially suppressed in comparison with M-Planck? And then the answer is yes. Okay, so for this end, you have to take sufficiently large value of psi. So here, on this plot, you have psi. On this axis, you have a parameter which characterizes this higher dimensional operator. And then you find out that indeed, if you take psi large enough, then you can get a required hierarchy between the Planck scale and the Higgs field. There is no prediction, okay? You can take another operator, and then everything can fail, in the sense that you will get a Higgs wave of the order of the Planck scale. The action can be very, very large. But the point here is that there may exist UV completions, understood in this way, of gravity plus theory, in which this transition from the Planck scale to lower scale is exponentially suppressed. Okay, there are other theories in which there is another type of operator which it doesn't happen. So it tells us something about very, very high energies. Okay, there are other things which are kind of interesting here, which I'm not going to enter, which are associated with inflation. You can take exactly the same theory, and see whether another manifestation of Planck physics, such as inflation, can take place. And then the answer is yes. And it's interesting that these two things are coherent in the sense that the constraints to this parameter psi coming from inflation are similar to that coming from this consideration. So I'm coming to my conclusions. So I would say that conjecture that there is just one scale in nature in Planck and that Fermi scale is generated dynamically from it may actually work. And the reason why Fermi scale is much smaller than the Planck scale may be rooted in conformal symmetry and non-perturbative gravity effects. And I will just show a couple of other slides very quickly because this is often asked. So here I took the standard model plus gravity without any extra particles such as grand unified theory, super heavy right-handed neutrinos, and one can wonder what explains origin of neutrino masses that matter better in the symmetry of the universe, cosmological inflation. The answer is kind of very simple. That could be new particles which with the masses below the Fermi scale. And so if you just take the standard model and expand it with the 3 right-handed neutrinos, then you can solve all these problems in a pretty natural way. Thank you very much for your attention.
So today we have Professor Mariano Quiros with us. So let's start our brief interview. Mariano, could you please explain to us briefly the main subject addressed in your talk?
Okay, I will do it, and I need a little introduction for
Sure,
general
okay.
people. No?
Be free. Yeah.
Okay. First, to say that in particle physics, which is my domain, and everybody else, as you, there is a well-established theory, which is called the Standard Model. The Standard Model is the theory of photons, electrons, quarks, and so on, which is well confirmed by all past and present experimental data, mainly by data at the Large Hadron Collider at CERN. However, we know that there must be physics beyond the Standard Model, so new physics, because the Standard Model cannot explain some experimental data as the presence of dark matter and dark energy and the baryon asymmetry of the universe, and has some theoretical issues, as for instance, the hierarchy problem, which is to understand why the vacuum of the electroweak theory is not destabilized by higher scales, as for instance, where the Planck scale, which is the scale where quantum gravity takes place. So one of the beyond the Standard Model theories aiming to solve the hierarchy problem was proposed in the United States in 1999 by Lisa Randall and Raman Sundram by introducing an extra warp space dimension. So it's a 5th dimension, it's an extra dimension with respect to our 4 dimensions, which are flat. This one is not flat. And then this could provide an explanation of the difference between the Planck scale and the scale at which present experiments are done at LHC, at CERN. In fact, 2 of those experiments at LHC, in particular Atlas and CMS, are making an exhaustive search of this new physics, which could confirm the existence of new physics beyond the Standard Model. On the other hand, this is one thing. On the other hand, a few years ago, a series of ground-based interferometers, like they are in the US and in Europe and Italy, have been able to find the gravitational waves, which is the carrier of the quantum excitation of gravity, a phenomenon already anticipated by Einstein's theory of general relativity. And in the future, ground-based interferometers, in particular, for instance, the Einstein's telescope, and satellite-based interferometers, for instance, LISA, are being planned to detect gravitational waves in around, let's say, 10, 15 years. So in my talk, I have presented possible detection of new physics with a warp extra dimension in the present and future interferometers, based on the stochastic gravitational wave background generated by the first-order phase transition experience from a deconfined Higgs to a confined Higgs. This is the phase transition when the temperature of the universe is decreasing. In this way, in my talk, I wanted to present an alternative to higher and higher energetic collider for the detection of a particular kind of new physics, which is associated to a strong first-order phase transition. So this is more or less the subject and the goal of my talk.
Okay, so you have previous experience regarding the Corfu Summer Institute, and tell us some about the workshop that your talk was actually presented.
Okay, so concerning my previous experience, the answer is yes. I have been attending very often the Corfu Summer Institute. Unfortunately, this time I couldn't attend presentially this institute because of restriction related to the COVID-19 pandemic.
Okay, I understand, yeah.
I wanted to emphasize, yeah, sure, yes. Some people, yeah, this was the case for some people. I wanted to emphasize that as soon as the pandemic situation will recover, I will attend the next Corfu Summer Institute with great pleasure. Moreover, soon the whole reconstruction of buildings in this set of Mont Repos will be completed. And I think that it will be open up a whole spectrum of new opportunities. Mont Repos, in my opinion, Mont Repos can hopefully become a hub of science where not only conferences and a school will take place, but also it can be used for smaller workshops and discussion meetings where physicists can gather and discuss new projects leading to important research outputs, hopefully. The new phase of the possible Corfu Institute scientific activity, in my opinion, is really exciting. It's such a great place. And about this, the current workshop, so the list of participants, around 150, and the number of conferences, more than 100, was really impressive. There were review talks, mainly updating the situation of fields, both from experimentalists and theorists, and there were specialized talks, which were many of them cutting edge in their respective fields. So the environment was really ideal to exchange ideas and promote new projects participated by people from different research centers. So very, very good opinion about the current workshop. Yeah.
Okay, thank you. And what is your suggestion to young scientists starting doing research?
Okay, that's a good point. That's a good point. So to young students, I have to say that research is a very rewarding activity. So perhaps not with money, I have to say. It is true that they have to work very hard and that the competition is sometimes tough, but the activity is so exciting that it is worth doing it. The general interest in research becomes clear when some big problem appears at the global level. For instance, we have seen as a pandemic, for instance, and this is concerning biologists and medical doctors, or a volcano eruption taking place as those days in La Palma in Spain. And this is concerning geologists and volcanologists. But do not forget that fundamental science, or in particular physics, is on the basis of all knowledge, that no applied science can take place without audience to enroll in research, either in applied, experimental, or theoretical science. They will discover how exciting can this activity be. That's my opinion. Okay, first of all, thank you very much for the invitation to speak online. I wish I could be there, but it was impossible. Okay, so the subject of my talk is a continuum solution to the hierarchy problem. So it's a little bit of change with respect to the previous talk, but okay, let's go. Oops. Okay, so what solution to the hierarchy problem? It was proposed, as everybody knows, by Lisa Randall and Raman Sundram in more than 20 years ago. And as you know, was based on a 5-dimensional space with anti-de Sitter geometry with line element given by this expression. This y is the extra coordinate in proper coordinate. And the metric in those coordinates is just linear in the proper coordinate. So there are two branes on this space. This is cut off by two branes, one the UV brane or Planck brane, and the other one the infrared brane or TV brane. And the typical scale in each brane, rho, is the, let's say the TV scale is related to the scale at the UV brane, which is typically K. K is related to the curvature of the anti-de Sitter. By this word factor. This word factor has to be around 30 something just to achieve the proper hierarchy. Okay, so then you can use the ADS-CFT correspondence to understand some phenomena. And that's very useful normally. So for instance, there are fields which are propagated in the bulk and which are localized toward the IR brane. In particular, they are the Higgs, they are the heavy fermions, and they are the Kaluza-Klein resonances. They are localized toward the IR brane, and in the language of CFT, okay, you can say that they are composite or almost composite. And on the other hand, fields which are localized toward the UV brane, the Planck brane, and are the light fermions, and they are essentially elementary. So this is just the language. This is just only the language. And of course, zero mode gauge bosons are flat in the extra dimensions. So this is just the theory. So you have a tower of KK resonances, which are on the TV scale, and then you have to probe this theory experimentally, and that's okay. That's the origin of the problem. So this is what I call collider challenges. For instance, people have studied the production of tops, a pair of tops, TT bar, and they are not finding the signal, and as a consequence, the LHC data are putting severe bounds on the mass of the slightest KK resonances, in particular here for KK gluons. And those are two plots from on the right-hand side from Atlas, and on the left-hand side from CMS. Both of them put bounds on the first KK resonance, which are, as you can see, of the order of 4 TeV for KK gluons. So that's really, well, okay, that's a sort of problem, because these limits point toward the possibility that nature might have chosen values of rho. Rho is the typical scale, which is perhaps much larger than TeV, or that we have to reformulate our model. So I will now present two ways of doing that. Way number one is just that those strongly coupled resonances as KK gluons, perhaps they are not narrow, but they are broad resonances. So in that case, bumps flatten in detection, and they are more difficult, very difficult to detect. This is the way number one. The way number two, which I will devote most of the talk, is that resonances are really a continuum of resonances. So in fact, there are no bumps at all. Okay, so those are the two possibilities. Okay, so this is what I will study now. So I will study a class of 5-dimensional models This is the class that we have considered, and then they share some properties. In particular, you can see this is the metric. It has two components. First, the Randall-Sundrum metric, and then a deformation which is very important in the infrared. So the properties of this metric, this is just a solution to the equations of motion. They reproduce Randall-Sundrum in the ultraviolet, and therefore they can explain conventionally the hierarchy problem with a fundamental Planck scale and a warped TV scale. So from that point of view, is nice. It depends on a parameter nu here that you can see. For nu larger than 1, they yield a discrete Kaluza-Klein spectra with TV spacing, which is the normal situation. For nu smaller than 1, they yield the continuum spectra without any gap, ungapped, and those are similar to unparticles that were proposed by Howard Chorchay some years ago. And then for the critical value of mu equals to 1, they yield a continuum spectra with a gap. So the critical case mu equals 1 is just very special because it gives a continuum with a mass gap. So the Green's functions, in that case, they generalize in the case of particle propagators. So the particle propagators, they have a real part, which in that case is the principal value of the propagator, and then an imaginary part, which in that case is just the delta function. In our case, what we will have is that the Green function has a real and an imaginary part. And the imaginary part is only valid, is different from 0 only for values of p squared, which are larger than the gap. Actually, this is the behavior of gapped unparticle, where the gap was usually produced by electroweak breaking. Here, the gap is the TV, so it's linked to the solution. Sorry, it's linked to the solution of the hierarchy problem. And just to make it clear, the 5-dimensional dimension has a UV boundary, an IR brane where the Higgs lives, and then there is a singularity at some value of the proper coordinate that I'm calling YS. And the mass gap is different for different bulk fields. So if you just take the different fields that will propagate in the bulk, you have gauge bosons, you have fermions, and you have graviton, radion, and the Higgs. So the mass gap is a function of rho, which is just this TB scale that I defined previously. And for the gauge boson, it is 1/2 of rho. For the graviton, radion, and Higgs is 3/2 of rho. And for the fermion, it depends on the constant C, which is the constant which determines the localization of the fermion. So C smaller than 1/2 corresponds to heavy fermions. C larger than 1/2 corresponds to light fermions localized towards the IR brane. So in that case, the mass gap for the fermion depends on this constant. The point is that one can explore the structure of Green's functions in the complex S-plane. That's very interesting because what you will find is that all Green's functions are inversely proportional to a universal function that I call here phi, which is just a combination of J plus and Y plus, where J plus and Y plus are combination of Bessel functions, as you can see here. And this function square root with some square root which gives branches to the complex S-plane. So using that, you can look for resonances by looking for poles in the second Riemann sheet of the complex S-plane. So unexpectedly, we have found a tower of broad resonances located in the physical Riemann sheet. And this is the contour plot for the function phi, where you can see the location of the zeros. The zeros of phi are the poles of the Green function. And this is just a very good approximation where the location of the poles in the complex plane can be given in terms of the nth branch of the Lambert function, as it is written down here. So there are no poles found in the first physical Riemann sheet. So the poles are interpreted as resonances. So we are finding really resonances. And those are the location of resonances where this is the mass in units of rho, and this is just the gamma over m. So the location of the masses is very similar to the Randall-Sundrum theory, while the effect of unparticle is just dressing those resonances to provide them with a width which is very, very wide, very broad for the first resonances, but then it goes down to smaller values. Conclusion. So warp extra dimension is an interesting alternative to solve the hierarchy problem. There is no doubt of that. One exploring possibility, as I mentioned, to solve the elusiveness of signal at LHC is that KK modes are very broad, triggered by fermions, localized towards the air brane. Another most intriguing possibility is that there is a continuum of KK states related to CFT and particles and so on. In particular, the 5-dimensional model with a continuum is pretty unique. As we have seen, it corresponds to a critical value of the metric parameters. And in fact, it is a 5D modelization of a conformal theory with a mass gap. Green's functions, as we have seen, behave like those of unparticles, which means that they have an imaginary part not corresponding to particle creation. And in general, Green's function can be decomposed as an unparticle component and Green's function with broad resonances, which Paul in the second Riemann sheet of S. As I said, the location of masses is very similar to that in the Randall-Sundrum model, while the width is very broad for the first resonances, while for heavy resonances it's narrow. As I said also, confronting this theory with LHC experimental data is in progress. And there are also plenty of theoretical problems to be understood. There is some work in progress here, and for instance, unitarity of the theory, spectral densities, and things like that. So this is really a new field that needs to be explored, although many things have already been done in the past. And so, okay, so thank you very much for your attention. Thank you.
So we would like to hear first some the highlights of your talk in a simple way.
Yes, very good. So basically the research I'm doing is based on looking for signs for new physics. We have this standard model of particle physics, and so we are looking at CERN in particular to find hints to know how to complete this standard model and how to go beyond. And since a few years, at one of the experiments at CERN, we are seeing some deviations from the standard model predictions, in particular at LHCb experiment. And so my talk will be about how to understand and interpret those data and what we learn from it in terms of hints for new physics.
Thank you very much. That was very nice and short because we don't have enough time. The next point I would like that you comment is what is your impression for what we do in Corfu. You have seen several meetings and you have seen the program. We have this social program. You saw yesterday this excellent performance, and we have the boat trip, Greek night. You have not been?
Yes, I have been there. Yes.
Okay. So what is your impression?
Yeah, so I think this place is really amazing. It's very good to gather people with the same patient in the same place, and also having all these young students among us. So I think it's very inspiring, and it gives opportunity to discuss, to meet colleagues, to do a lot of also talking about different projects, and also
in a relaxed way.
In a relaxed way, exactly, and also in a very friendly way. So I think it's very useful both for senior physicists and also for young scientists. And the place is really nice. I think it's the effort that you are making here to have this center is really, really valuable. So I really appreciate it.
Thank you very much. And what you would advise to all these young people? We don't have so many women in physics, but we have some good ones like you.
Thank you.
What you will advise to the young researchers?
Well, it's hard to have any advice. Perhaps what I can say is to young people, that's what I say also to my students, is to follow their passion. I think doing physics, doing science in general, it's a great pleasure. And we do science for satisfying our curiosity. And I think this is, I mean, you don't do it for money, and
you do it for fun.
We do it for fun, for pleasure of learning and understanding how things work. So I think it's my only advice. Follow your passion.
Very good. Thank you very much. Can you hear me all right? Yes, good. So let me start by thanking the organizers for their very kind invitation. It's a great pleasure to be here. It's a great pleasure to be out of Zoom, finally, and participate in a real meeting. So thank you very much. But perhaps the most intriguing hint for new physics is from lepton flavor universality ratios. So here, for example, you have this RK ratio, which is basically the ratio of B to K star mu mu over the same thing with electrons. And so here we have the LHCb measurements, which is from 2017 with 3 inverse femtobarn of round 1 data. And this was measured in 2 low Q squared mean, so very low Q squared mean and low Q squared mean. And in both means, the standard model is prediction is very close to 1. And you can see that the experimental measurements are below 1 significantly. And so the tension is at the level of 2.2 and 2.5 sigma in the 2 bins. So here what is interesting is that these ratios do not depend on any hadronic uncertainties, because everything cancels out basically. There was also the measurement of RK, so lepton flavor universality, this time in B2K LL, so B2K mu mu over B2K EE. And this was measured in 2014 for the first time, showing 25% deviation from SM predictions. Here, the standard model prediction is very accurate with the error below per mean level. And so this is the latest experimental measurement, which was released in March using the full data set of LHCb, which shows a 3.1 sigma deviation from the standard model prediction. Very good. Now we can look at 2 operator fits, so assuming new physics in 2 coefficients at the same time. So here you have different sets, for example, C9 mu, C9e, C9 mu, C10 mu, C10 mu, C10e, and here you have the chiral basis. But you can see here that the latest fit corresponds to the colored region. So you have the 1 and 2 sigma green region, which is the result of the fit to all available data until now, that you can compare with the round 1 results, which was this black contours. So as you can see, even in these 2 operator fits, the pool SM is for these sets are above 7 sigma, and here it's 4.5 sigma. And compared to what we had before in, let's say, by 2019, you see that the significance of the tensions increased by about 2 sigma. So previously it was about 5 sigma, now it's about 7 sigma. And these are delta C9, so standard model predictions corresponds to 0 here each time. Now let's have a look at the prospects in the 2-dimensional fit. Again, using only the clean observable. So this is in the plane C9 mu, C9e, and this is in the plane C9 mu, C10 mu. that's the situation of the fit with the current data. Now this is how it changes when you go to 18 inverse femtobarn of data, 15 inverse femtobarn of data, and 300 inverse femtobarn of data. So as you see, this the 2 sigma region shrinks by a lot, which means also that the deviation with the standard model increases also by a lot. And now my time is up, and I will jump to my conclusion. As I said, the latest LHCb measurements still show persistent tensions with the standard model predictions in B2SLL transitions, which are growing actually in both statistical significance and internal consistency with time and with more data. Compared to round 1 data, with the updated data, the hierarchy of the preferred new physics scenarios remain the same with increased significance. And fit to clean observables and the rest of PSLL observables point to compatible new physics scenarios. This is a non-trivial consistency checks, let's say, because these measurements are completely different, and also the theoretical treatment of these decays are also different. And assuming the central values of the current fits with already 18 inverse femtobarn of data, significances above 6 sigma can be reached with only clean observables. And the LHCb upgrade will have enough precision to distinguish between different new physics scenarios. Thank you.
What did you say? What is the highlight of your talk?
Okay, well, it's nice to be here, George, and to be with you again. I've been 3 or 4 times, and it's a lovely, well-organized conference. My talk, I gave a talk yesterday. It was about an extension of the standard model, which has a simple idea of replacing the group SU2 by the group SU3. And this has 2 benefits. One is it can explain why there are 3 families, which is a big mystery, one of the biggest mysteries of the standard model. And the second property it has is that the new physics, the new particles, have to be at most a few TeV. This is quite unusual in model building. So the new physics is restricted to that. The big test, which is being done at CERN as we speak in 2021, is to find a doubly charged gauge boson, we call the bilepton, in the, for example, mu plus channel. And if that is found, assuming that it's found, which will be a confirmation of 331, then what I talked about yesterday is the fact that because there are new quarks, beyond the 6 we know, there would be 3 more heavy quarks around a TeV with unusual charges and properties. And these will be bound into additional baryons and mesons, which will be much heavier than the ones we know, starting at a TeV up to perhaps 9 TeV. And the reason this is interesting at CERN is it will give a scientific justification to build a bigger collider. Yeah, that was a general idea. I mean, I guess you don't want technical details. Yeah.
The other question is, you told us already, what is your impression in general of what we are doing here? I mean, about the program and how we bring people here. And,
well, you have a good international audience, and I've been 3 or 4 times. And yesterday afternoon, after my talk, I talked to about half a dozen students in their 20s doing PhDs, and it was very interesting. They were asking about what sort of things to work on, and it was very refreshing that they're interested in particle phenomenology, of the original kind, and getting less interested in these what I would call distractions of string theory and supersymmetry, which have been around now for decades and haven't produced any successful predictions.
Well, about supersymmetry, I could give you something, but this is not me to talk, it's you to talk.
Oh, you have a prediction,
and,
yeah.
we have good predictions for the top quark and for the kids.
Oh, okay, yeah.
So, since you started already, what you would advise of these young people? Is it a good period?
Yes, I think it's a good period. Well, we have to rely on the data, but if CERN finds new particles, for example, the one I talked about, or others, then I predict that there will be many, many new states and new physics, and therefore
many interesting things to
discover in the next decade or two, and it will be a revival of particle theory. So I would recommend they work on phenomenology of particles, including neutrinos and so on.
And they should work hard, I suppose.
And work very hard on their own ideas, and if they work hard enough, they will succeed. Okay, so I want to thank the organizers, particularly George Stefanos, for the invitation. And it's very appropriate this is in the QCD section, because I think I've only ever written 2 papers on QCD in my career of almost 500 papers, and this is the second one. The first one would be chiral color, I suppose. But this, what I'm talking about in this presentation turns out to be correct. And for the moment, it is a speculation. It will mean that there's a very promising future for QCD and the quark model for the 2020s and the 2030s, because I'm going to speculatively predict that there are a huge number of additional baryons and mesons at energies which can be reached probably only with the FCC. Although the key signature that this is correct is accessible to the LHC, and in fact, as Albert Dweck briefly mentioned in his talk, the key signal is to find the bilepton, which is a doubly charged resonance in like sign leptons. So this is what could be regarded as the most likely first beyond the standard model particle, and it is being searched for both at ATLAS and CMS, according to what I hear from CERN. And the key model, the model can be called the bilepton model. Originally, I called it the 331 model, but that has caused confusion because it's not enough to have the gauge group SU3 cross SU3 cross U1 as a generalization of SU3 cross SU2 cross U1, but it also has to have particular assignments for the fermions and the charge operator and so on. Now, I don't have time in this talk to explain the background of this. I think I've talked about it before in this conference. But in making an extension of the standard model, there are an infinite number of possibilities, but one would like it to be motivated by answering a question which is within the standard model and testable by explicit predictions. The bilepton model has 2 things in its favor. One is that it explains the existence of 3 families, which is one of the biggest mysteries in the standard model. And it explains that by a particular way of canceling the triangle anomalies, which fixes the various fermion and gauge bosons And it is testable. Equally important, perhaps more important than the explanation of three families, is that this particular model from 1992 has the property that the new physics must be at a few TeV. It cannot be pushed up to arbitrarily high level, for a reason I don't have time to explain, but that's a peculiarity of this model, which means that the new physics should be accessible to the LHC, at least some of it, but what I'm going to talk about will inevitably require more energy from the LHC, for example, in an FCC. So as well as these extra quarks, we have 5 extra gauge bosons, because SU3 has 5 more generators than SU2. One of them is a Z prime, which is not terribly interesting because it's very, very broad with a width comparable to its mass. But the other 4 are called bileptons, and they are either doubly charged or singly charged. The singly charged are harder to find because they decay into neutrinos, but the ones that are easy, as a theorist, I can say easy, but unquestionably it's difficult for the CMS and Atlas, but possible, I am told. These bosons have lepton number 2, and they decay into same-sign leptons. The best mass estimate I made with Mariano, 1.29 TeV. This mass estimate is not sharp, but that's roughly where it should be, let's say 1300 GeV. And so this is being looked, this particular particle is being searched for at CERN as we speak. And as an optimist, I hope it will be discovered in 2021. Then everything I'm going to say after this will be a sharp prediction. At the moment, it's a speculation. So let's take this model for the moment as correct so that I can go on. Then physics for the next 10 or 20 years becomes very exciting because you have a whole panoply of additional hadrons unsuspected by anybody until today, unless you've been reading my papers. So these extra quarks have these peculiar charges, and of course QCD will bind them into baryons and mesons. They will bind with the light quarks and with each other. And so let's briefly, for the next 15 minutes, discuss these baryons and mesons. Let's suppose these new quarks have a hierarchy of mass P bigger than S bigger than D by comparison with the light quarks. And as I mentioned, one very important point of this model is that these quarks cannot be arbitrarily heavy. They must be below a magic scale of about 4 TeV, 4.1 TeV, because this is a reason I don't have time to explain in detail, but it's all to do with embedding SU2 cross U1 and SU3 cross U1, which is possible only if the energy is below this, because above this, it will violate unitarity, because one of the couplings will become imaginary. That's very unusual in model building, because in almost every model I've ever built, the scale can, like in supersymmetry, for example, the scale can go up arbitrarily high. This one cannot. So let's just take a look at the mesons and baryons. I'm going to exhibit only half of them, and the charge conjugates go without saying. Oh dear. Can anyone see that? Well, let me just indicate what it is. So, oh, good. Yeah, if you keep doing that, that will help a lot. So let's take a heavy quark with a light quark, large antiquark. So this is a meson. Now, one peculiar thing, one of the several peculiar things, is that these heavy quarks are, as usual, they're color triplets with spin a half and so on, but they carry lepton number, which is a new property of this model. And this means that these new mesons carry lepton number. In this case, either +2 or -2. And of course, they have these multiple charges. So the charges of the mesons are -2, -1, +1, +2. So let's assume that the masses follow this inequality. And so we have a certain hierarchy of possible masses. So the lightest of the TeV baryons and mesons are those containing just one capital D quark or one capital D antiquark. And the next heaviest contain one S quark or one S antiquark, and so on. Now, the decays of these heavy quarks are typically into a light quark plus a bilepton. For example, D into usual D plus Y minus. And that Y minus, the predominant decay mode of the bileptons, is into 2 leptons with lepton number 2. So you have, for example, electron plus anti-electron neutrino, not anti-electron neutrino, and so on and so forth. And so if we go to the hadronic scale, hadronic language, then this particular meson, this would be one of the lightest new mesons, will decay into a pi minus and 2 leptons in one of the 3 families. And there are variants, there are flavor of variants. And we can replace, for example, the D up here with, of course, it can decay into a U and Y minus minus and so on. Yes, that's what I just said. So D, capital D into U plus Y minus minus, and the Y minus minus, this is the thing they're looking for at the LHC, is the Y minus minus will go into 2 like sign leptons. At LHC, probably, or almost certainly, the easiest one to see is mu minus plus mu minus. Now, I should emphasize that all these tables are purely speculative, and you can forget them immediately unless the LHC finds, the easiest thing to discover seems to be the bilepton, which is the doubly charged gauge boson in like sign leptons. We have our fingers crossed that that will show up in 2021. I'm an irrational optimist, but there's at least one other particle theorist who seems to think that might be true. And then once that happens, all these 5 tables will become a sharp prediction. These things will have to exist. And our experimental friends will have to find them and build an FCC and find them with that. I hope to be alive when the FCC finds them. What's the soonest the FCC could run? 20 years? 2060? Well, I'll only be 117. 2060, I'll be 117 years old. It's a question for biology more than physics. Can't you speed it up a little bit? Anyway, that's, thank you for your attention.